Unit 11 is about exponential and log functions. These are also functions you should have seen in Algebra 2. So, looking first at what an exponential function is, by definition, an exponential function has the variable in the exponent. So on these, your y equals e to the x is going to be a very basic one, with e being the base. E is a value 2.718 that is like pi, it's just an irrational number. For what we're going to do, your base can be anything. As long as your variable is in the exponent. Now your graphs that you should be familiar with of exponential functions, this first one that is increasing would be a function that is your most basic parent function. This one is also referred to as exponential growth in applications because it is doing just that. It is growing. The other version of this graph that I have is what we call exponential decay. And there's a couple of different ways to vary your equation to get the graph to do this. It is a reflection over the y-axis. So we can do something as simple as making the exponent negative. Now on these, as far as your characteristics that you need to be familiar with, in any of these equations that have different bases, all create the same basic graph. The steepness with which represents how fast they increase is what will change. So our domain for exponential functions is going to be all real numbers. So we have no limit on the x values that can be plugged in. Your range is going to be limited by horizontal asymptote. So every exponential function is going to have a horizontal asymptote. So your range is going to be, for the parent function, from 0 to infinity. If you have any kind of vertical shift up or down, that's going to shift that horizontal asymptote. So that would be determined by the k value in your equation. Your key point on these, the two things that you're going to use to graph, are the horizontal asymptote, which is at y equals 0, again for the parent function, or y equals k if there's been a vertical translation, and the y-intercept. So your y-intercept on these is going to be at 1. So if you have any kind of vertical translation, you want to look for your intercept being 1 unit above your horizontal asymptote. And our end behavior we'll look at the growth function. So we're looking specifically at this one. For the decay function, they would just switch. So on the left-hand side, our function is approaching that horizontal asymptote, so that's going to be 0. On the right-hand side, we are increasing without bound, so it is going to infinity. Log functions are in a set of functions that we label as transcendental functions. These transcendental functions are functions that can't be explained using addition, subtraction, multiplication, or division. So your log function is basically just a way to undo an exponent. So your equations on these, just like the base can change for your exponential functions, your base can change for your log functions. So if you have just log of x, then there's an understood base of 10. You could have log base 2 of x. Your base is a subscript, so it needs to be written small, lower than your log. And if we have a base e, then we're using ln for natural log. And very similar to the exponential function, the graphs of these are going to vary by how quickly they increase, and that's determined by what your base is. The rest of the characteristics are going to be the same. So our graph of our log function looks like this. Our domain is going to be limited this time. By a vertical asymptote. So our domain is going to be from 0 to infinity for our parent function. And this one will be impacted by our horizontal movement. So if we have a shift left or right, that's going to move that asymptote. So that would be controlled by our h. The range on this one is all real numbers. So we have no limit on the output. Your x-intercept is going to be at 1. And again, it should be 1 unit to the right of your vertical asymptote. Our vertical asymptote is going to be at 0. Again, that will change if we have a horizontal shift. We can talk about the limit as x is approaching the asymptote from the right-hand side. So we're approaching 0 from the right, and that would be going to negative infinity. Our end behavior, remember if we have a vertical asymptote and there is no graph at all on the left-hand side, as x approaches negative infinity, we'll write does not exist because the graph does not exist on that left side as x is getting closer to negative infinity. On the right-hand side, our function is unbounded, so it goes to infinity. So as far as the graphs and what you need to know, we're not going to do a whole lot of work with all the transformations with these because they're hard to see on the graphs because the graphs of all the different functions are very similar. So you need to make sure you know the basic shapes of the graphs and their domain and range and their asymptotes. Now, getting into evaluating some basic logarithms that you need to know the values of. Without a calculator, you should just know these when you see them. Anytime that you have an argument, so whatever we're taking the log of is called the argument. If that is a 1, then your answer is going to be 0 because that represents your intercept. Now, the basic exponents that you need to know that are listed kind of underneath, anything to the 0 power is equal to 1. So because of this relationship, this is true. And we'll talk about converting back and forth in just a second. Anytime you are taking a log and your base and your argument are the exact same, the value is 1. And that is because any base raised to the first power stays the same base. Log of 0, if you look at your graph for logs, log of 0, that's where our vertical asymptote is. So anytime you have an argument of 0, that log is undefined. Same is true for log of negative numbers. Natural log of 1, again, this guy being a 1 right here, automatically a 0. Doesn't matter what the base is. Natural log of e is one you need to recognize. The natural log has an understood base of e. So this is going to be a similar situation as this. So because the base and the argument are the same, this is going to equal 1 every time. Exponents. So we've talked about these two. Anything to the -1 power. This is just one of your exponent rules that you should already know. A negative exponent means that we can move that base to the denominator. The value of the exponent doesn't change, so it'd still be b to the first, but by moving it denominator, numerator, you can lose the negative in the exponent. Logs and exponential functions are related because they are inverse functions. One undoes the other. So that is why we teach them together, because in order to solve log equations, we have to use exponents. In order to solve exponential equations, we have to use logs. So our log form and our exponential form, you need to be comfortable converting between the two forms. So your log form log base b of x is equal to y. And our exponential form that corresponds would be b to the y is equal to x. So I'm going to go back and color code a couple of things. So the base of the log and the base of the exponent are the same. The base is the base. The other two pieces are going to switch places. So the argument, whatever we're taking the log of, comes out of the log. So this is why it's used to solve, is because if I have an equation that looks like this log, or this x, is stuck inside the argument of this log. The only way to get it out of there is by rewriting it in exponential form. And the answer to the log is the exponent on the exponential. So if we were to have an exponential function where this y was unknown, the only way to get that y out of the exponent is by taking the log. So you need to be very comfortable switching between log form, going from log to exponential, and going from exponential back to log. I have a couple of examples that I'm going to show you for what you're going to do in your practice today. So the first example, to rewrite in exponential form, so I'm going from log to exponential. So the 2 is my base. The 32 is the argument of the log. And the 5 is the answer. So when I go to put it in exponential form, my base is going to be 2. My power is going to be the 5. And 2 to the 5th is equal to 32. So this relationship between these two functions is what can't be described using addition and subtraction. It's just a pattern that somebody found. So recognizing the pattern is what you need to be able to do. Rewriting in log form, same idea. So my base is 7. My exponent is the x, and it's equal to 49. So on this one, if this was values that I didn't know what x was, right now that x is stuck in the exponent, and there's no way to get it out of the exponent in a productive way other than to convert it to log form. So since our base of the exponent is 7, we'll convert that to log base 7. 49 will become my argument of the log, and it will be equal to x. So on these, again, I'm just rewriting them. So going from one format to the other. There, for example, 3, evaluate without a calculator. So on these, the logs, thinking of it in terms of exponents is really beneficial. So log base 3 of 27, I want to think about 3 to what power would equal 27. And that's going to be 3. Because 3 times 3 is 9, 9 times 3 is 27. Log base 2 of 1/2. So if I have 2 to what power equals 1/2. Well, the only thing that can move a base from top to bottom is by changing the exponent to negative. So that is 1/2 to the first. So the exponent that I need on the 2 would be a -1. So this is the type of things you'll have to do in the practice today. If you have questions, we can go over those next week.